In the last chapter, we developed sequential logic, which contains both combinational logic and memory components. The combinational logic cloud is an acyclic graph of components that obey the static discipline. The static discipline guarantees if we supply valid and stable inputs, then we will get valid and stable digital outputs by some specified interval after the last input transition. There's also a functional specification that tells us the output values for every possible combination of input values. In this diagram, there are k plus m inputs and k plus n outputs. So the truth table for the combinational logic will have 2 to the k plus m rows and k plus n output columns. The job of the state registers is to remember the current state of the sequential logic. The state is encoded as some number k of bits, which will allow us to represent 2 to the k unique states. Recall that the state is used to capture, in some appropriate way, the relevant history of the input sequence. To the extent that previous input values influence the operation of the sequential logic, that happens through the stored state bits. Typically, the load input of the state registers is triggered by the rising edge of a periodic signal, which updates the stored state with a new state calculated by the combinational logic. As designers, we have several tasks. First, we must decide on what output sequences need to be generated in response to the expected input sequences. A particular input may, in fact, generate a long sequence of output values, or the output may remain unchanged while the input sequence is processed, step by step, where the FSM is remembering the relevant information by updating its internal state. Then we have to develop the functional specification for the logic so it calculates the correct output and next state values. Finally, we need to come up with an actual circuit diagram for the sequential logic system. All the tasks are pretty interesting, so let's get started. As an example sequential system, let's make a combination lock. The lock has a 1-bit input signal where the user enters the combination as a sequence of bits. There's one output signal, unlock, which is 1 if and only if the correct combination has been entered. In this example, we want to assert unlock, in other words, set unlock to 1, when the last 4 input values are the sequence 0, 1, 1, 0. Mr. Blue is asking a good question. How many state bits do we need? Do we have to remember the last 4 input bits? In which case, we need 4 state bits. Or can we remember less information and still do our job? Aha! We don't need the complete history of the last 4 inputs. We only need to know if the most recent entries represent some part of a partially entered correct combination. In other words, if the input sequence doesn't represent a correct combination, we don't need to keep track of exactly how it's incorrect. We only need to know that it is incorrect. With that observation in mind, let's figure out how to represent the desired behavior of our digital system. We can characterize the behavior of a sequential system using a new abstraction called a finite state machine, or FSM for short. The goal of the FSM abstraction is to describe the input-output behavior of the sequential logic, independent of its actual implementation. A finite state machine has a periodic clock input. A rising clock edge will trigger the transition from the current state to the next state. The FSM has some fixed number of states, with a particular state designated as the initial or starting state when the FSM is first turned on. One of the interesting challenges in designing an FSM is to determine the required number of states, since there's often a trade-off between the number of state bits and the complexity of the internal combinational logic required to compute the next state and outputs. There are some number of inputs used to convey all the external information necessary for the FSM to do its job. Again, there are interesting design trade-offs. Suppose the FSM required 100 bits of input. Should we have 100 inputs and deliver all the information at once? Or should we have a single input and deliver the information as a 100-cycle sequence? In many real-world situations, where the sequential logic is much faster than whatever physical process we're trying to control, we'll often see the use of bit serial inputs, where the information arrives as a sequence, 1 bit at a time. That will allow us to use much less signaling hardware at the cost of the time required to transmit the information sequentially. We'll describe the operation of the FSM for our combination lock using a state transition diagram. Initially, the FSM has received no bits of the combination, a state we'll call SX. In the state transition diagram, states are represented as circles, each labeled for now with a symbolic name chosen to remind us of what history it represents. For this FSM, the unlock output U will be a function of the current state, so we'll indicate the value of U inside the circle. Since in state SX we know nothing about past input bits, the lock should stay locked, and so U equals 0. We'll indicate the initial state with a wide border on the circle. We'll use the successive states to remember what we've seen so far of the input combination. So, if the FSM is in state SX and it receives a 0 input, it should transition to state S0 to remind us that we've seen the first bit of the combination of 0, 1, 1, 0. We use arrows to indicate transitions between states, and each arrow has a label telling us when that transition should occur. So this particular arrow is telling us that when the FSM is in state SX and the next input is a 0, the FSM should transition to state S0. Transitions are triggered by the rising edge at the FSM's clock input. Let's add the states for the remainder of the specified combination. The rightmost state, S0110, represents the point at which the FSM has detected the specified sequence of inputs, so the unlock signal is 1 in this state. Looking at the state transition diagram, we see that if the FSM starts in state SX, the input sequence 0, 1, 1, 0 will leave the FSM in state S0110. So far, so good. What should the FSM do if an input bit is not the next bit in the combination? For example, if the FSM is in state SX and the input bit is a 1, it still has not received any correct combination bits, so the next state is SX again. Here are the appropriate non-combination transitions for the other states. Note that an incorrect combination entry doesn't necessarily take the FSM to state SX. For example, if the FSM is in state S0110, the last 4 input bits have been 0110. If the next input is a 1, then the last 4 inputs are now 1101, which won't lead to an open lock. But the last 2 bits might be the first 2 bits of a valid combination sequence, so the FSM transitions to S01, indicating that a sequence of 01 has been entered over the last 2 bits. We've been working with an FSM where the outputs are a function of the current state called a Moore machine. Here the outputs are written inside the state circle. If the outputs are a function of both the current state and the current inputs, it's called a Mealy machine. Since the transitions are also a function of the current state and current inputs, we'll label each transition with the appropriate output values using a slash to separate input values from output values. So, looking at the state transition diagram on the right, suppose the FSM is in state S3. If the input is a 0, look for the arrow leaving S3 labeled 0/. The value after the slash tells us the output value, in this case 1. If the input had been a 1, the output value would be 0. There are some simple rules we can use to check that a state transition diagram is well formed. The transitions from a particular state must be mutually exclusive. In other words, for each state there can't be more than one transition with the same input label. This makes sense. If the FSM is to operate consistently, there can't be any ambiguity about the next state for a given current state and input. By consistently, we mean that the FSM should make the same transition if it's restarted at the same starting state and given the same input sequences. Moreover, the transitions leaving each state should be collectively exhaustive. In other words, there should be a transition specified for each possible input value. If we wish the FSM to stay in its current state for that particular input value, we need to show a transition from the current state back to itself. With these rules, there will be exactly one transition selected for every combination of current state and input value. All the information in a state transition diagram can be represented in tabular form as a truth table. Let's think a bit more about the FSM abstraction. If we see an FSM that uses k state bits, what can we say about the number of states in its state transition diagram? Well, we know the FSM can have at most 2 to the k states, since that's the number of unique combinations of k bits. Suppose we connect 2 FSMs in series, with the outputs of the first FSM serving as the inputs to the second. This larger system is also an FSM. How many states does it have? Well, if we don't know the details of either of the component FSMs, the upper bound of the number of states for the larger system is m times n. This is because it may be possible for the first FSM to be in any of its m states, while the second FSM is in any of its n states. Note that the answer doesn't depend on x or y, the number of input signals to each of the component FSMs. Wider inputs just mean that there are longer labels on the transitions in the state transition diagram, but doesn't tell us anything about the number of internal states. Finally, here's a question that's a bit trickier than it seems. I give you an FSM with 2 inputs labeled 0 and 1, and 1 output implemented as a light. Then I ask you to discover its state transition diagram. Can you do it? Just to be a bit more concrete, you experiment for an hour pushing the buttons in a variety of sequences. Each time you push the 0 button, the light goes off if it was on. And when you push the 1 button, the light goes on if it was off. Otherwise, nothing seems to happen. What state transition diagram could we draw based on our experiments? Consider the following 2 state transition diagrams. The top diagram describes the behavior we observed in our experiments. Pushing 0 turns the light off, pushing 1 turns the light on. The second diagram appears to do the same thing, unless you happen to push the 1 button 4 times in a row. If we don't have an upper bound on the number of states in the FSM, we can never be sure that we've explored all of its possible behaviors. But if we do have an upper bound, say k, on the number of states, and we reset the FSM to its initial state, we can discover its behavior. This is because in a k-state FSM, every reachable state can be reached in less than k transitions, starting from the initial state. So, if we try all the possible k-step input sequences one after another, starting each trial at the initial state, we'll be guaranteed to have visited every state in the machine. Our answer is also complicated by the observation that FSMs with different number of states may be equivalent. Here are 2 FSMs, one with 2 states, one with 5 states. Are they different? Well, not in any practical sense. Since the FSMs are externally indistinguishable, we can use them interchangeably. We say that 2 FSMs are equivalent if and only if every input sequence yields identical output sequences from both FSMs. So, as engineers, if we have an FSM, we would like to find the simplest, and hence the least expensive, equivalent FSM. We'll talk about how to find smaller equivalent FSMs in the context of our next example. Surprise! We've just been given a robotic ant that has an FSM for its brain. The inputs to the FSM come from the ant's 2 antennae, labeled L and R. An antenna input is 1 if the antenna is touching something, otherwise it's 0. The outputs of the FSM control the ant's motion. We can make it step forward by setting the F output to 1, and turn left or right by asserting the TL or TR outputs respectively. If the ant tries to both turn and step forward, the turn happens first. Note that the ant can turn when its antennae are touching something, but it can't move forward. We've been challenged to design an ant brain that will let it find its way out of a simple maze like the one shown here. We remember reading that if the maze doesn't have any unconnected walls, in other words, no islands, we can escape using the right-hand rule, where we put our right hand on the wall and walk so that our hand stays on the wall. Let's try to implement this strategy. We'll assume that initially our ant is lost in space. the only sensible strategy is to walk forward until we find a maze wall. So our initial state, labeled lost, asserts the F output, causing the ant to move forward until at least one of the antennae touches something. In other words, at least one of the L or R inputs is a 1. So now the ant finds itself in one of these three situations. To implement the right-hand rule, the ant should turn left, counterclockwise, until its antennae have just cleared the wall. To do this, we'll add a rotate counterclockwise state, which asserts both the turn left output until both L and R are 0. Now the ant is standing with a wall to its right, and we can start the process of following the wall with its right antenna. So we have the ant step forward and right, assuming that it will immediately touch the wall again. The wall 1 state asserts both the turn right and forward outputs, then checks the right antenna to see what it should do next. If the right antenna does touch, as expected, the ant turns left to free the antenna and then steps forward. The wall 2 states asserts both the turn left and forward outputs, then checks the antenna. If the right antenna is still touching, it needs to continue turning. If the left antenna touches, it's run into a corner and needs to reorient itself so the new wall is on its right, the situation we dealt with the rotate counterclockwise state. Finally, if both antennae are free, the ant should be in the state of the previous slide, standing parallel to the wall, so we return to the wall 1 state. Our expectation is that the FSM will alternate between the wall 1 and wall 2 states as the ant moves along the wall. If it reaches an inside corner, it rotates to put the new wall on its right and keeps going. What happens when it reaches an outside corner? When the ant is in the wall 1 state, it moves forward and turns right, then checks its right antenna, expecting to find the wall it's traveling along. But if it's an outside corner, there's no wall to touch. The correct strategy in this case is to keep turning right and stepping forward until the right antenna touches the wall that's around the corner. The corner state implements this strategy, transitioning to the wall 2 state when the ant reaches the wall again. Hey, this might even work! Let's try it out. Meet the RoboAnt simulator. On the left, we see a text representation of the transition table for the FSM brain. Each action line specifies an input pattern, which, if it matches, will set the next state and output signals as specified. This particular version of RoboAnt allows the ant to drop or pick up breadcrumbs and to sense breadcrumbs it comes across. These inputs and outputs aren't needed for this demo. The input pattern specifies a value for the current state and antenna inputs. The simulator highlights the row in the table that matches the current inputs. As you can see, initially the ant is in the lost state with neither antenna touching. On the right is a map showing our green ant standing in a maze with blue walls. We can select several different mazes to try. To see the ant in action, let's click the step button several times. After a few steps, the ant hits the wall, then rotates counterclockwise to free its antenna. Now it starts following the wall until it reaches a corner, at which point it keeps turning right and stepping until it's once again. Earlier, we talked about finding equivalent FSMs with fewer states. Now we'll develop an approach for finding such FSMs by looking for 2 states that can be merged into a single state without changing the behavior of the FSM in any externally distinguishable manner. 2 states are equivalent if they meet the following 2 criteria. First, the states must have identical outputs. This makes sense. The outputs are visible to the outside, so if their values differed between the 2 states, that difference would clearly be externally distinguishable. Second, for each combination of input values, the 2 states transition to equivalent states. Our strategy for deriving an equivalent machine with fewer states will be to start with our original FSM, find pairs of equivalent states, and merge those states. We'll keep repeating the process until we can't find any more equivalent states. Let's try this on our ant FSM. First, we need to find a pair of states that have the same outputs. As it turns out, there's only one such pair, wall 1 and corner, both of which assert the turn right and forward outputs. Okay, let's assume that wall 1 and corner are equivalent and ask if they transition to equivalent states for each applicable combination of input values. For these two states, all the transitions depend only on the value of the R input, so we just have to check two cases. If R is 0, both states transition to corner. If R is 1, both states transition to wall 2. So both equivalence criteria are satisfied, and we can conclude that the wall 1 and corner states are equivalent and can be merged. This gives us the four-state FSM shown here, where we've called the single merge state wall 1. This smaller equivalent FSM behaves exactly as the previous 5-state FSM. The implementation of the 5-state machine requires 3 state bits. The implementation of the 4-state machine only requires 2 state bits. Reducing the number of state bits by 1 is huge, since it reduces the size of the required ROM by half. Just as we were able to achieve considerable hardware savings by minimizing Boolean equations, we can do the same in sequential logic by merging equivalent states. RoboAnt customers are looking forward to the price cut. Let's look at what we'd need to do if we wanted to implement the FSM using logic gates instead of a ROM for the combinational logic. First, we have to build the truth table, entering all the transitions in the state transition diagram. We'll start with the lost state. So if the FSM is in this state, the F output should be 1. If both antenna inputs are 0, the next state is also lost. Assigning the lost state the encoding 0, 0, we've captured this information in the first row of the table. If either antenna is touching, the FSM should transition from lost to the rotate counterclockwise state. We've given this an encoding of 0, 1. There are 3 combinations of L and R values that match this transition, so we've added 3 rows to the truth table. This takes care of all the transitions from the lost state. Now we can tackle the transitions from the rotate counterclockwise state. If either antenna is touching, the next state is again rotate counterclockwise. So we've identified the matching values for the inputs and added the appropriate 3 rows to the transition table. We can continue in a similar manner to encode the transitions one by one. Here's the final table, where we've used don't cares to reduce the number of rows for presentation. Next, we want to come up with Boolean equations for each of the outputs of the combinational logic. In other words, the 2 next state bits and the 3 motion control outputs. Here are the Carnot maps for the 2 next state bits. Using our K-map skills from Chapter 4, we'll find a cover of the prime implicants for S1 prime and write down the corresponding product terms in a minimal sum of products equation. And then do the same for the other next state bit. We can follow a similar process to derive minimal sum of products expressions for the motion control outputs. Implementing each sum of products in a straightforward fashion with AND and OR gates, we get the following schematic for the AND brain. Pretty neat. Who knew that maze following behavior could be implemented with a couple of D registers and a handful of logic? Okay, it's finally time to investigate issues caused by asynchronous inputs to a sequential logic circuit. By asynchronous, we mean that the timing of transitions on the input is completely independent of the timing of the sequential logic clock. This situation arises when the inputs arrive from the outside world, where the timing of events is not under our control. As we saw at the end of Chapter 5, to ensure reliable operation of the state registers, inputs to a sequential logic system have to obey setup and hold time constraints relative to the rising edge of the system clock. Clearly, if the input can change at any time, it can change at a time that would violate the setup and hold times. Maybe we can come up with a synchronizer circuit that takes an unsynchronized input signal and produces a synchronized signal that only changes shortly after the rising edge of the clock. We'd use a synchronizer on each asynchronous input and solve our timing problems that way. Here's a detailed specification for our synchronizer. The synchronizer has two inputs, in and clock, which have transitions at time Tn and Tc respectively. If in's transition happens sufficiently before c's transition, we want the synchronizer to output a 1 within some bounded time Td after clock's transition. And if clock's transition happens sufficiently before in's transition, we want the synchronizer to output a 0 within time Td after clock's transition. Finally, if the two transitions are closer together than some specified interval Te, the synchronizer can output either a 0 or a 1 within time Td of clock's transition. Either answer is fine, so long it's a stable digital 0 or digital 1 by the specified deadline. This turns out to be an unsolvable problem. For no finite values of Te and Td can we build a synchronizer that's guaranteed to meet this specification, even when using components that are 100% reliable. But can't we just use a D register to solve the problem? We'll connect in to the register's data input and connect clock to the register's clock input. We'll set the decision time, Td, to the propagation delay of the register, and the allowable error interval to the larger of the register's setup and hold times. Our theory is that if the rising edge of in occurs at least T setup before the rising edge of clock, the register is guaranteed to output a 1. And if in transitions more than T hold after the rising edge of clock, the register is guaranteed to output a 0. So far, so good. If in transitions during the setup and hold times with respect to the rising edge of clock, we know we've violated the static discipline, and we can't tell whether the register will store a 0 or a 1. But in this case, our specification lets us produce either answer, so we're good to go, right? Sadly, we're not good to go. We're lured by the digital abstraction into assuming that even if we violate the dynamic discipline, that Q must be either 1 or 0 after the propagation delay. But that isn't a valid assumption, as we'll see when we look more carefully at the operation of the register's master latch when B and C change at about the same time. Recall that the master latch is really just a lenient mux that can be configured as a bistable storage element using a positive feedback loop. When the latch is in memory mode, it's essentially a two-gate cyclic circuit whose behavior has two constraints. The voltage transfer characteristic of the two-gate circuit, shown in green on the graph, and that Vin equal Vout, a constraint that's shown in red on the graph. These two curves intersect at 3 points. Our concern is the middle point of intersection. If in and clock change at the same time, the voltage on Q may be in transition at the time the mux closes and enables the positive feedback loop. So the initial voltage in the feedback loop may happen to be at or very near the voltage of the middle intersection point. When Q is at the metastable voltage, the storage loop is in an unstable equilibrium called the metastable state. In theory, the system could balance at this point forever, but a small change in the voltages in the loop will move the system away from the metastable equilibrium point and set it irrevocably in motion towards the stable equilibrium points. Here's the issue we face. We can't bound the amount of time the system will spend in the metastable state. Here's what we know about the metastable state. It's in the forbidden zone of the digital signaling specifications, and so